So yeah, like I said, welcome back to this class. This is where I want to start. I'll let you guys take a minute in the chat, and I want you to tell me each of these, it's a metal, a metalloid, or a semi-metal, or a non-metal. So tell me which of these is which, and I'll be back in 1 minute, and you can type it in the chat. Okay, so the question was, I'm back to recording now. The question was, how do we know the difference between non-metal and semi-metal, or even metal and semi-metal? Well, basically, it's kind of like a process of elimination. I told you that only one of these, like I said, we'll have all three of them in this list. So if you look at this list, a chemical that has a poor luster, it could be a semi-metal or a non-metal. It's definitely one of the two. Substance B is malleable and ductile. That is definitely a property of a metal. So substance A has properties of both metals and nonmetals, and it actually has the same properties of that semiconductor I just showed you on the last slide. And we know that semiconductors are semi-metals or metalloids. So if you guys in the chat, oh yes, question?
Yeah, sir, we find out like from the table, yeah?
Yes, you find out from the table and from the information that I showed you about semiconductors.
Yeah, so like substance, it is like something inside the table, yeah? We need to follow it.
Yes.
Yeah, also.
Yeah. Yep. Okay. So now that I know that I have my semi-metal there, and for you people in the chat who said metalloid, you would get 100 mark, 100% full marks. Metalloid is fine. But now, if we go down to these two, since I know that this is a semi-metal, substance B has to be a metal because non-metals are brittle, and substance C has to be a non-metal. Poor luster means it's not shiny. So this is a non-metal. Cool. All right. Now, I wouldn't focus on that too hard, but you might see a multiple choice someday on your test or final exam where I might say, this chemical is malleable, ductile, and a shiny gray substance. And, what do you think it is? Metal, non-metal, metalloid, and then none of the above or something, right? So if I told you it was malleable, ductile, solid, and gray, or solid and shiny, it's definitely a metal. All right. So let's get to where I am in the other class. This won't take too long. I really think I need to edit some of these slides. There is a lot of extra information in this next section. So I'm going to show you the information that you guys need to know for any upcoming labs or quizzes or tests. So, oh, hold on. Oh, okay, everything's good. Okay, so first things first. The periodic table, a couple things I want to mention about this. This slide actually has something really important I want to mention. I'll just kind of read it, but there's something important topic hidden inside this. Elements in the same group. Now remember, groups go up and down. They are the columns, right, up and down. Elements in the same group have similar chemical properties, not all the same, but very similar. So the alkali metals have similar properties. For example, they're very reactive with water. The noble gases have similar properties. For example, they are not very reactive. So elements in the same group have similar properties, but physical properties are not the same. They don't really match in the groups. Physical properties, it's really important to know what I mean by this, because physical and chemical properties are not the same thing. So a physical property is a physical description. The color, the smell, right, or odor, the density, the temperature. Oops.
But sir, the smell not like chemical.
Nope, smell is not chemical.
Oh, okay.
Yeah, and physical is just a physical description. So, you know, what does it look like? What does it smell like? What is the shape? Oops. Ah, I hate this pen. For it to be chemical, it has to have some sort of reaction. We're talking about a chemical reaction here. Chemical property would be related to its reaction or reactivity. So some examples of chemical properties would be, I'm just going to list them here. Reacts with water, reacts with oxygen. What else could we say? It is poison or toxic. It is flammable. Okay, so why are these, especially like the last two, what makes them different than physical? Well, poison or toxic refers to a chemical reaction that a chemical will have with your body. When you ingest a toxic substance or poison, it on a cellular, on a biological level, the chemicals react with your body. So a smell is more of how your body perceives something. It's not as much as a reaction as it's your receptors picking up on this smell, sending the signal to your brain. Your brain says, oh, this smells like banana, this smells like chocolate. It's not as much as a chemical reaction like poison. When you drink or eat something that's poison, sometimes they can, drastically break down cellular activity or have, block certain activities in your body. You guys know I'm not a biologist, but something being toxic is definitely a chemical reaction. Oh, I have a really good question in the chat. I'll get to that in a second. And flammable is definitely a good chemical property because flammable is a chemical reaction called combustion. So some things aren't flammable, right? Water is not flammable. You can't put a lighter or a match on a bucket of water. It's not going to, and expect to flame. But something like an alcohol like methanol or something, or a hydrocarbon like propane, very flammable. Um, Acid or base are chemical properties. That's a good one, Shadan in the chat. That because we'll learn a little bit more about this later. Acids react. Acids are called acids because of how they react. Bases are called bases because of how they react. So that's a great one. And Abdulhalim had I think I said your name right, had a really good one, maybe one of my favorites. He asked, are melting and boiling points chemical or physical? What do you guys think? Melting or boiling point, chemical or physical?
Chemical.
Okay, anybody, any other guesses? And I'm not saying you're wrong, I'm just saying any guesses.
Chemical, teacher.
Sorry?
Chemical.
Chemical, okay. I'm getting mixtures because in the chat I'm getting chemical, and or on the mics I'm getting chemical, in the chat I'm getting physical. Okay. You guys, this is why I fell behind, because you guys asked so many good questions. This is a fantastic question. Okay, so I'm getting stuff in the chat here. I'm getting physical, chemical, whatever. All right, here's the thing. Oops, sorry. My PowerPoint is giving me issues. I'm leaving you guys in suspense. The answer is physical. So why does, like, and I know what you're thinking. You're thinking, hold on. If, it's melting or boiling, that's got to be chemical. But really, the answer to this is quite simple. Physical, melting and boiling. So the question is why? For a chemical reaction to happen, you have
both of them.
You have to make a new chemical. That's it. So I want you to think of, in the kitchen, Okay, the easiest example is to think of a kitchen, in the kitchen. You take where am I going to start? You take a glass of water in the kitchen and you freeze it. Okay, it turns into ice cube, so solid. So I have water, I have ice, and now what if I do the opposite? What if I take that water and I boil it? Well, then you get what's called steam. But it's still H2O. In every situation here, it's still the molecule H2O. And again, I can really explain this even more. You guys can do this in your kitchen right now. You can take water, you can freeze it, then let it melt, then boil it with the lid on, put the lid on, let all the water collect on the top, then let it cool down back to a liquid, then freeze it, and you can go back and forth 1,000 times. It's still H2O. It's never a new chemical. And I see something going on in the chat, but I just want to raise one more question. So consider that you could freeze and boil ice and water and back and forth and back and forth. And now think of cooking a piece of toast or frying an egg. Okay? If you cook toast or cook a pizza in the oven, there is no way to turn that pizza back into an uncooked pizza. It will be brown forever. The cheese will be melted. The cheese will be browned. Maybe an egg is the best way. Crack an egg, you have a see-through white. I know it's called the white, but it's see-through. You have a yellow yolk that's runny. When you cook an egg, it's done. You cannot uncook that egg. Chemically, it has changed. But with water, you can cook it, freeze it, boil it, and it will always be the same. Yeah, you should. I mean, you could do it. I mean, you don't need to do it, but you could think about it too, because I mean, just next time you're at the movies and you have a drink and you think about that ice melting, think about when you're at the movies and you have this nice fresh Pepsi or Coke or whatever, and it tastes so good. And then 30 minutes later, all the ice is melted and it tastes watery.
Yeah.
It's
So
just
Joe, this one physical, yeah?
physical. Oh yeah, up at the top, physical. And the reason your drink tastes watery is because it's not a new reaction. It's just water in your drink. So I really, really like that question because, you know, you ask the average person, is boiling or melting chemical or physical? It is physical. Cool. Okay. Yes.
So I have a question.
Yeah.
So when we do a chemical reaction and we got a new substance with different color in this moment, it's a chemical reaction. So why you put it as a physical?
You guys, you ask such good questions. Okay, that's a great question too. So, okay, let's think about it. We talked about this in the lab last week. You see a color change, and a color change tells you that it's a chemical reaction. So what's going on there? Why is it like? Why am I telling you that physical is color is a physical description? Well, I can explain. Okay, say you have chemical A. Its physical description, sorry about my pen there, guys. Physical description is clear and colorless. Oh, I hate this pen so much. You then turn it into chemical B somehow. You do, again, remember the definition of a chemical reaction is taking A and turning it into B. That literally, that's what chemistry is. When you make new bonds, you make a new chemical, it's chemistry, or it's a chemical reaction. Okay, so let's say you turn A into B and your physical description is it's now white and cloudy. Okay. These are physical descriptions. Okay. But the fact that its physical description changed tells me that a chemical reaction happened. So what is getting mixed up here is the definition of a physical description, chemical description, or chemical reaction. This is definitely a chemical reaction, And I know it's a chemical reaction because my physical description changed. I know that might be a little hard to kind of think about. It's kind of like a, I wouldn't say philosophical question. No, it's not, but it's kind of, it can sound a little tricky, but that's the answer. If you are watching a chemical reaction happen and the physical description changes, so again, going back to physical descriptions, if the smell changes, if the temperature changes, if the color changes, if these physical descriptions change, it's a chemical reaction.
Yeah, sir.
Yes, sir?
Yeah, sir. For example, if we put like a color for mixing with the water, okay, it is a chemical reaction, yeah?
What do you mean?
Like if I have a color and I mix it with the water.
So like if you mean,
Okay.
if you took like,
Like same in the lab, what we do, like we mix the color inside the water and it gives like a reaction chemical, like changing of the color, yeah.
if you mix a chemical with water and the color changes, that's
Yeah.
chemical. That's chemical.
Yeah, but if the color not changing, it will be a physical, yeah?
Well, it's no reaction, so nothing happened. Yeah.
No reaction, okay.
Yeah. Yep. Cool, cool, cool. Okay. All right. It's 5-3 and I haven't even started yet. But this is wonderful. I have no complaints. But I do have to just cover a couple things today, guys, so we can get out of here. But I really love all of these questions. It's fantastic. So let's get moving on. I think I'm still going to be a little behind, but that's okay. If I can at least get through these two today and maybe introduce this one, we will be okay. But if I can get through 2 topics today, and this will be really quick because the density is like 1 sentence is all you need to know. So what I mentioned at the beginning of the class, a lot of my notes have extra information that you don't need. So I will show you today in the next 15 minutes what exactly you need to know, because these slides have a lot, like look at all this information. Not all of this you are expected to know. It's just kind of interesting. All right, so let's start with density. Oh, and yes, question?
Is it density same as the efficiency? It's look like same.
I don't think so. Do you mean like the Greek letter? Is that what you're talking about?
Efficiency, like oil density.
Oh, yeah. Well, I mean, oil density and density would be the same. Yes. Yeah. Yeah, for sure. Efficiency for oil and gas. I'm just kind of Googling that now. So efficiency. Okay, so sorry, and I'm researching this or I'm looking this up because I should know this. Efficiency is how efficient your fuel is, meaning when you burn the fuel, how much is lost or wasted when it's converted into energy. So the more efficient a fuel is, the better it will burn, the more energy you get. We can talk about that later. I really do have to move on, but I don't think efficiency of oil and density are the same. Efficiency is related to the combustion reaction and how much energy that you get. But I do have to move on. But that is a really good question. So before I get into density, I do want to mention what this word means, trend. A trend is like a pattern. And when I hear the word trend, I think of like fashion or cars or even sometimes like movies or food trends. I know when I was growing up in university, there was a coffee shop on every corner where I lived, coffee everywhere. And then 10 years later, all of those coffee shops turned into sushi shops, like sushi bars. And then 10 years later, I went home last summer and now it's all like tapas and tacos and little like small bites of like kind of Spanish food or even I guess South American food. I know that they're not close on the globe, but there's a relation there. So a trend is like a pattern that you see. And it could be fashion as well. You know, what are the people in Hollywood wearing this year? It's a pattern or something that you'll notice. And a Twitter, exactly, Mohammed. I'm an old man here, see, and I should have said that first. It's like anything trending on Twitter. Why didn't I think of that? So when you see a hashtag or something trending, everybody's talking about it. There is a pattern, and the periodic table is the exact same. There is a trend on the periodic table of properties, and we are going to look at 4. And guys, for your test or final exam, you should know these 4 only. If you look at the periodic table, what type of trend would you see about the size of atoms? What type of trend would you see for the energy it takes to make an ion? So very quickly, I'm going to do the first 2. Now, unfortunately, some of you in my class here today might have missed their lab this week. The lab this week was called density. This has nothing to do with your lab. So if you missed your lab this week, like you were told to stay home, you're obviously excused, but don't worry. It has nothing to do with this at all. So you will not, like, don't worry. This is about the trend of density on the periodic table. If you're curious and you missed the lab this week, density, I shouldn't say you missed it. You didn't really miss it. You weren't allowed to come, which is not your fault at all. But if you didn't come or weren't allowed to come, density is the mass of an object divided by its volume. And all elements have different densities. So for example, like if I had a liter of, I'm going to say oxygen, and I had a liter of gold. Actually, I'm going to change it from oxygen because like oxygen is a bit hard to picture in your head. Let's take a liter of water, okay, 1,000 milliliters of H2O. I know this is not an element, but like, what do you guys think would weigh more? A liter of water or a liter of gold? What would weigh more?
Water, teacher.
Water, more than gold.
No, gold. It's solid.
Well, yeah, I mean, gold is solid. You could melt it as a liquid, but this is an experiment you guys could do at home today. I will warn you, be very careful with this. If any of you have gold in your house, like you might have a gold ring or a golden necklace or something.
Full width, teacher.
Pick it up, put it in your sink, make sure the sink is closed, of course, like put the closure down and drop the ring in your sink. It will sink, it will not float. Gold is much more denser than water.
We can try it, teacher, and
yeah, just don't lose your ring. Don't lose your ring. But it doesn't need to be a gold ring. You take anything. I mean, go to your kitchen and grab a spoon. It's probably made out of carbon and iron, stainless steel. I should say iron and carbon. Just like metals tend to sink in water because they are way more dense. So gold here would have way more mass per volume. So gold is the answer. This would be much more dense. I think it's 10 times more dense than water. So it would weigh 10 times what a liter of water weighs, I think. Anyways, that doesn't matter because you know what? This is not about what density is. This is about the trend. And guys, this is the trend that I want you to know. This is it right here. That's all you need to know on top. Density generally increases as the atomic number increases. So as we increase protons and protons and protons, the atoms are getting larger and larger and larger. Now, density is not related to size, for example. It's just, I'm just saying that when we increase the number of protons, we increase the density. And this has to do to intermolecular forces. We'll do this in unit 3. Okay, we'll come back to that later. Metals typically have higher densities than non-metals, but really all you need to know for this slide, this trend, is that density increases as atomic number increases. So if I gave you guys a list of atoms, so here's hydrogen, that's number 1. Oh, this pen. Here's carbon, that's 6. neon is 10, aluminum is 13. Which of these would be the most dense, or sorry, have the highest density? Hydrogen, carbon, neon, aluminum.
Aluminum.
Aluminum, thank you. Aluminum is the most dense. Perfect. That's it. That's all you need to know. How simple is that? And if I had something even higher, like iron, which I can't remember, it's like 34, 33, something like that, 30 something, iron would be more dense. Gold is like 80 something, 82. I can't remember these numbers. I used to know. Gold might be 79. Anyways, the bigger this number, the more dense it is. All right, that's it.
Sir?
Yes?
So there is no question that will ask us to like calculate the density, right?
No. Just I would have a multiple choice, and I would say, which element is the most dense, A, B, C, or D? And the answer is D. Well, and you know what? The key to this is you have to say, or I would have to say, which element should be the most dense. Because remember, trends are not always 100%. Trends follow a pattern. So guys, what I'm telling you today isn't always true. It's typically true. So we're basically using the power of the periodic table to help make us very, very good and reliable predictions. But there's always exceptions. But it's not about that. It's about making predictions. And most of these predictions are very accurate. Okay, give me just a couple. Yes?
Sir, how about one element with different isotopes? Do they have the same density?
Ooh, that's a good question. So the question is, you got the same element. I assume you mean the same element, like if we had carbon and we had different isotopes of those carbons, which would be the most dense? I don't actually know, but I'm going to use an educated guess to say that the higher the mass number, the more dense it would be. Because if you look at isotopes of any element, they would have the same, this is good, they would have the same atomic radius because the electrons aren't changing. I'm getting ahead of myself now, but to answer your question, if you had to figure out which isotope was the most dense, it would be the one with the higher mass number because it has a bigger mass, but it would have still the same volume. That was a good question. And I assume I'm right. I'm using an educated scientific guess. I have never seen that written down anywhere in my life, but I think I'm right. Okay, so let's move on here. I have one more thing to show you, and then that'll be it for today. There is a lot of information, guys, on the next 2 slides, and I don't really want you to worry too much about that information. I'm just trying to explain to you one thing. When you're trying to talk about the radius of an atom, that is a very hard concept to discuss. So let me start off by telling you the simple definition. I'm going to try something new here today, guys. I'm going to try my highlighter. Oh yeah, that's nice. Look at that. That's cool. Okay, this is what you need to know, what I've highlighted. The other information is really interesting, which I will explain very quickly, but what you guys need to know is that if I ask you, what is an atomic radius? You should tell me, well, it's the size of an atom. That's it. It is the size of an atom. That is your definition. Okay, even simple. Look, I'll use my red pen. The size of the atoms. That's it. Now, I do want to very quickly mention something. Calculating the radius of an atom is not like calculating the radius of a wheel or a pizza or a circle in real life. And I'm not saying atoms aren't real. What I'm saying is the boundary of an atom is not well defined because atoms really are like what's surrounding the nucleus here are electrons that are floating around it in like this cloud of probability. It's not actually like a circle, like a pizza. So there are two ways to look at radius, and I'm going to go really quick. Guys, this is all you need to know. You don't need to know the rest. Just make sure you know that the atomic radius is the size of the atom. However, there are two ways to look at the atomic radius. There's the way that, there's the way that I would think of when I think of a circle or a sphere. You take the center of that thing, which is the nucleus, and you measure the distance to the outside. That's your radius. Remember in math, guys, the difference between diameter and the difference between, radius. Okay, oh my gosh, my pen. Radius is half the diameter. This is not math class, so don't worry about that. The other way some scientists measure the radius is they measure the distance between two nucleuses that are bonded together and then split it in half. It's half this number. You guys do not need to know this. This is just extra information. So what do you need to know? You need to know that the atomic radius of a chemical element is the size of the atom. The other thing you need to know is our trend. And the trend is, as we go down the periodic table, I guess we go down the column, and we go left across the period, the radiuses, the elements, the atoms, I should say, get bigger. So as we go down and left, the atoms get bigger. So let me just explain this. Like, this is a hard graph to look at. These numbers are the, calculated radiuses. The unit, I do believe, is quite small. Angstrom, I think, unit for atomic radius. Picometers. Yeah, I don't know why my brain said angstrom. Picometers. So times 10 to the minus 12 would be like these numbers. They're very, we typically measure the atomic radius so small. They're very tiny. So this is a cool graph. The taller the bar is, right? The longer the bar, the bigger the atom is. So like helium is pretty small, 0.32, neon 0.69, argon 9.7, krypton and xenon get bigger. So here's what you want to do, or what you want to maybe think of. When I show you a flat periodic table, whoa, I didn't know that was going to happen, sorry. Okay, when I show you the flat periodic table, I'm going to pick another color here. The trend is this way. Oh, my pen's getting worse, guys. I don't know if you've noticed that, but it's getting worse. It's a brand new pen. Look at that. Look at that. Oh my gosh. So increasing radius. Okay, ignore my pen. Don't worry about those lines. It's the increasing radius. So if I asked you, very simply, like what atom do you think would be bigger? Up here, we'll take my good friend, I love neon, versus something down here like rubidium, right? Which would be bigger? Well, rubidium would be bigger. There's a lot of factors here, guys, about why the atoms are bigger. The simple answer is, rubidium has way more protons, like way more. Let me open up a periodic table. I don't have all these memorized, sorry. Rubidium, what are you doing there, rubidium? Rubidium has 37 protons. Neon has 10 protons. Rubidium has 37 electrons. Neon has 10 electrons. So obviously, rubidium is going to be much bigger. So why does it increase going this way? That's something we're going to talk about a little bit later. But you do need to know this trend, that as we go down and left, the radii or the radiuses of the atoms, the size of the atoms get bigger. So the biggest atom on the periodic table is down here, and the smallest would be up here. Helium, or of course, hydrogen. All right, I'm gonna read the chat, and I got one more thing to say, and I'm done. And yeah, I'm always, oh, that's true too, Hamza. You guys can always help me draw. You could, you know, the funny thing is if I use my finger, or if I used a stylus, like a little pen you would use on your phone, it would work fine. The Surface Pen is cool because I can use the eraser on the back. There's buttons, like the pen is amazing. It's just, I get these weird little lines. Anyways.
You saw actually draw right now. Actually do something right now on your left.
Oh yeah, exactly. I mean, that's maybe, well, in my chemistry 2420 class, I get them to draw sometimes. I get them to draw the shape of molecules, and I'll get them to use their finger, or some of them are using iPads so they can use like a pen and just draw. So yeah, I'm not opposed to that sometime. But
yeah, it's good. But then in case you're tired or something, if you want someone to volunteer and stuff.
Oh, for sure. Although I am always tired though. But yeah, for sure. Maybe I'll ask someone to help me some next time. Guys, I want to finish today. It's 3:14, and I really, really appreciate all the chatter, like the questions. I love this so much. This is like my favorite thing. I just want to mention, like, there's 3 slides here that are coming up: ionic radius, and ionic trends. Guys, the only thing you really need to know about ionic radiuses, and now think about the difference between an atom and an ion. Ions are a little more complicated because some ions are bigger and some ions are smaller. Like cations are smaller because they lose electrons. Anions are bigger because they gain electrons. Don't worry about this stuff. What you need to know is that the ionic trend is pretty much the same as the atom trend. So same trend, we're gonna go with the exact same trend. Oh, I knew the radii was angstroms, I'm not crazy. It's the same trend as atoms, okay? That's like, so if I ask you, you know, which would be the bigger ion or which would be the bigger atom, it's the same trend. It goes down and left, okay? Down and left. We'll do a little bit of more review on this tomorrow. I am still a little bit behind, which is fine, but tomorrow we'll talk about ionization energy. Actually, tomorrow, guys, we will finish chapter 2, I do believe. We'll get close to finishing chapter 2. So again, just to summarize, these 3 slides, don't worry about them, okay?
There is a quiz.
Know that it's the same trend. Okay, I'm going to answer your question, but first I'm going to stop recording. So if you guys want to go, have a great day. So, you know, goodbye. I'll see you tomorrow.